All right, so this first problem says a mole of ideal monoatomic gas. So monoatomic gas, that tells you whenever they say stuff like this, they're telling you CV and CP. CV is 3/2 R for monoatomic gas. Okay. CV is number of degrees of freedom divided by 2 times R. And for a monoatomic gas, the degrees of freedom is 3. And then CP is CV plus R. So this would be 3/2 R, 3/2 R, and that would be 5/2 R. Okay. Anyway, so mole of ideal monoatomic gas at 0 degrees Celsius and 1 atmosphere is warmed up to expand isobarically at constant pressure to triple its volume. How much heat is added during the transfer? It's an isobaric process, so the amount of heat added is NCP delta T. And for a monoatomic gas, this is 3/2 R, and this would be 3/2 plus 1/2, the 1, that is 5/2 R. All right, so it's 1 mole. Okay. And so now all you have to do is figure out how much the temperature rises. Okay. Now from the ideal gas law, PV equal to nRT. P is constant, change in volume equal to nR change in temperature. So change in temperature is P times change in volume divided by nR. Okay, what is the change in volume? The final volume expands to triple its initial volume. So all right, that's the volume, pressure remains constant, so it's equal to initial volume. And you see PV NR, okay, PV or NR is the initial temperature, which is given to be 0 degrees Celsius. Okay, so delta T, the change in temperature, works out to 2 times PIVI-NR, which is 2 times TI. Okay. All right, so now we'll plug that in here. So Q, the amount of heat added, is N times 5 by 2 R, and delta T was 2 times TI. All right, now we can plug stuff in. How many moles of gas you had? You had 1 mole of the ideal gas. Initial temperature is that. Okay. So 1 mole, 5/2. R is 8.314 joules per mole per Kelvin. 2 times. Initial temperature 0 degrees Celsius, which is 273 degree Kelvin. Okay. So that 2 cancels with that. So that's joules, that's how many joules you add. So 11.4 kilojoules of heat is added to warm that gas. Yep. Okay, this problem says an engine with an efficiency of 0.3 absorbs 500 joules of heat per cycle. How much work does it perform per cycle? Okay, so the efficiency is defined as work done for this much heat absorbed. Okay, so the work done is efficiency times the amount of heat absorbed. And so if you do work done per cycle, that's the heat absorbed per cycle. Yep. So the work done per cycle is, the efficiency is 0.3. Heat absorbed per cycle is 500 joules. 150 joules per cycle. Okay. And if you wanted to calculate the power is work done per unit time. So if you know how long it takes to complete one cycle, so if it takes half a second to complete one cycle, it would be, 150 joule divided by 0.5 seconds. That would give you 300 watts. Okay. All right. How much heat does it discharge per cycle? So QH is QC plus W. QC is the heat discharge and W is the work done. So QC is QH minus W. Okay. And QC per cycle is QH per cycle minus W per cycle. That's 500 minus 150 equal to 350 joules per cycle. Okay, so this is the story of heat engines. See, you're absorbing 500 joules. You're converting only 150 of that to work. And you're dumping out 350 joules every cycle. Okay? Okay, so heat is the worst form of energy. Try to convert it into work. You see the efficiency is only 30%. Okay? And like I said, the best practical heat engine, large-scale practical engine, is a coal power plant, and the efficiency is 40%. What happens to this heat? What did you do with it? Dumped it into the atmosphere, or a lake, or whatever. Okay? That's what happened. So, a coal power plant consumes 100,000 kg of coal per hour and produces 500 megawatts of power. If the heat of combustion of coal is 30 megajoules per kg, that is, if when you burn 1 kg of coal, and if you burn it entirely, then you get 30 megajoules of heat. So to burn coal entirely, they powder it and so on. Okay, so to make sure all of it burns. What is the efficiency of the power plant? The efficiency of the power plant is work divided by QH. Okay. Now, the power plant is producing electricity, but electricity to work conversion is almost 100%. Okay, so we'll assume that that's the work. Okay, so now what we really have is rate at which work is done. Okay, so we'll call it Power is work over time, so QH over time. Yeah. This guy is 500 megawatts. Okay, so let's figure out what this is. How much heat is generated per second? Okay, you're burning that much coal per hour. Okay, so QH by T is 10 to the power 5 kgs of coal and 30 megajoules of heat is released per kg, and that's in 1 hour. 1 hour is 3,600 seconds. Okay, so that's the rate at which you're producing heat. All right, so let's see. This is 10 to the 6, 3 times 10 to the 12, and 3 times 10 to the 9 divided by 3.6 joules per second. That is a gigawatt. Okay. So, coming back to the efficiency, efficiency is 500 megawatts divided by 0.83 into 10 to the 9 joules per second. Efficiency is a dimensionless number. Okay, so this is 0.5 divided by 0.83. Okay, this comes to the top, that becomes 10 to the minus 3. That's 0.5 divided by that. Okay. This is 0.6. The efficiency of this coal plant is 0.6, and that's a lie. Like I said, the best coal plant is about 0.4. Okay. So probably, well, to produce that much electricity, Hoover Dam is 1 gigawatt, twice that. Okay, a little more than that. So you probably have to burn about 30% more coal. Yeah. Closer to 140 tons per hour. Okay, this problem says a refrigerator discards 80 joules of heat per cycle. Okay, what does a refrigerator do?
Evaporates.
It takes heat from a colder temperature and dumps it there. Okay. Well. And how does it do? It has to do work. So now this diagram is QH is well, okay. TC, TH, it's removing QC, it has to do work, and QH that is being dumped is QC plus W. Okay, so that's what a refrigerator does. It takes heat from a cold temperature and puts it in a hot environment. Okay, of course you have to do work. So the instant you unplug the refrigerator, it would stop doing that. So the amount of heat it's dumping is 80 joules per cycle. Okay, that's what it's dumping into your kitchen. The coefficient of performance is 6. The coefficient of performance of the refrigerator is 6, which is how much heat did you remove from the cold environment and how much work you had to do for that, divided by how much work you had to do for that. So for every 6 joules of heat removed from your refrigerator, you had to do 1 joule of work. That's what that tells you. Okay? Okay. The quantity of heat it removes per cycle from the cold reservoir. Okay, so how much heat did it remove from the cold reservoir? Okay, so COP is QC minus W, and W is, so from this equation, W is QH minus QC. Okay. They tell you the coefficient of performance is 6, QC minus QH, and QH you know is 80 joules per cycle. So now QC is the only unknown, and you can solve it. Okay, so 6 8s are 48 minus 6 QC into QC. So the amount of heat removed per cycle is 480 divided by 7. And then they ask you how much work is done per cycle. And work done is QH minus QC. So work per cycle is QH per cycle minus QC per cycle. 80 minus 68.6. Work done per cycle is that. Okay, so you do 11.4 joules per cycle, and you remove almost 70 joules of heat per cycle. Okay. So as your refrigerator, as the inside of your refrigerator is getting cold, what is happening? Your kitchen is getting warmer. And so because your kitchen is getting warmer, what do you have to do? You have to turn on the air conditioning. And as the inside of your house is getting colder, what's happening? Very good. All right. So an engine operating between heat reservoirs at 20 degrees Celsius and 200 degrees Celsius extracts 1,000 joules per cycle from the hot reservoir. Okay, so a heat engine, so again, this is the cartoon diagram for the heat engine. You'll see this in your notes. This is the hot reservoir. So what does the hot reservoir mean? Where is the hot reservoir in your car? The cylinders. Again, the cylinders where the gas is burning. At that temperature, you're extracting heat, and you get some work out of it. So in your car, that work shows up as the motion of the car. And then you're dumping the heat that you cannot utilize via the exhaust into the atmosphere. Okay. So this heat engine is operating between these two temperatures. Okay. It extracts 1,000 joules per cycle. What is the maximum possible work the engine can do? Which engine does the maximum possible work? the ideal engine, which is called the Carnot engine. Very good. Okay. So the ideal engine can do the maximum work. Okay. So the Carnot efficiency is the maximum possible efficiency. Okay. And the Carnot efficiency just depends on the temperatures. Okay. And those temperatures are in the Kelvin scale. Okay. So the maximum possible efficiency is TC is 293 Kelvin and TH is 473 Kelvin. Okay, so the the Carnot efficiency of an engine operating between these two temperatures would be .38 okay. And so EC equal to W by QH, and so W is EC by QH. So this is the maximum work you could get out of this heat engine, and that's 0.38 thousand joules per cycle. I'm going to just give you rough numbers, okay? So this kind of stuff is real in the sense, okay, do you guys know what the US economy is? Huh?
Is it bad?
What?
Is it bad?
No, okay, so $30 trillion a year. Okay. And I'm just giving you rough numbers. It's roughly 10% of that is spent on energy, and most of it is gotten via fossil fuels. So 10% of 30 trillion is 3 trillion. Most of it, the energy comes from fossil fuels, again, rough numbers, and that's 30% efficient. So $2 trillion worth of heat is dumped into the atmosphere every year for the $1 trillion a year of electricity. This stuff is real. So if you go to a green economy, where all your electricity is coming from solar cells and wind energy, you're not doing that anymore. Yep.
What about part B of the last question?
I'm sorry?
Part B.
Yeah, what is for maximum work, how much heat is exhausted per cycle? Okay, so,
Okay, all right, sorry.
yeah. Okay, so B is QC would be QH minus W, so QC per cycle would be 1,000 minus 380. Okay. So this is the $2 trillion that I talked about. An ideal gas at 300 degree Kelvin is compressed isothermally to 1/5 its original volume. Determine the entropy change per mole of the gas. Okay, so you can look up your formula. It's log V final over V initial. Now, the gas is compressed, so it's compressed into a smaller volume. There's less disorder. Okay? So the entropy of the gas actually decreases. Okay? And they ask you determine the entropy change per mole of the gas. So what they're asking you is this, log V final over V initial. And the final volume is 1/5 its original volume. So R times log 1/5 V initial. And log of 1 is 0, so it's so in this process the entropy decreased. But I thought we said that the entropy of the universe never decreases. So are we lying here?
It's always increasing, but it can decrease eventually into a larger increase.
So when you did work, the entropy of the environment increased more than that. So the total entropy of the universe increased. All right. What is the entropy change of 10 grams of steam at 100 degrees Celsius when it condenses to water at the same temperature? Okay. So what you have is a bunch of steam at 100 degrees Celsius, and it goes into water at 100 degrees Celsius. Now this is a smaller volume, it's more ordered state, so the entropy has decreased. Okay. Change in entropy is the amount of heat absorbed at a given temperature. Okay. Now, when it goes from steam to water, it doesn't absorb heat, it gives up heat. How much did it give up heat? Minus the mass times the latent heat of vaporization. Okay. So 10 grams, and this is 10 grams, 540 calories per gram. That's the latent heat of vaporization. And we'll convert it into joules, 184 joules per calorie. And the temperature at which this is happening is 373 degree Kelvin. All right. Okay, so the change in entropy was negative 60.6 joules per Kelvin. So by the same token, if you boiled 10 grams of water to steam at 100 degrees Celsius, that would be the increase in entropy. If you went this way, the system entropy would increase by that much. Okay, this problem says 50 grams of water at 20 degrees Celsius is heated until it becomes vapor at 100 degrees Celsius. Okay. Calculate the change in entropy of the water in this process. Okay. Now, what you're doing is you're taking water from 20 degrees Celsius to 100 degrees Celsius and then turning into steam at 100 degrees Celsius. So you absorbed water you absorbed heat when you went from here to there, and then you absorbed heat in going for this phase change. Okay. The thing was when you were absorbing change in entropy in an infinitesimal process is how much heat you absorb divided by the temperature at which you absorb that heat. So in this process, the temperature is changing. Okay. So you have to take little baby steps, calculate that. So the change in entropy would be dq1 T1 plus dq2 T2 till you get to 100 degrees Celsius, and then you're absorbing heat at constant temperature. And then that would be mass times LV divided by that temperature. What is this? When you add a bunch of stuff, little, yeah. But you guys are very sophisticated, and that is an integral. Yeah. All right. When you warm water, how much heat are you adding? Let's see. So delta S is when you warm the water a small amount, that's how much heat you added. Okay, so that will be the change in entropy in this process, this integral. And what was the initial temperature? What is the limits for the integral?
20 to 100.
Okay, what are the limits?
20 to 100 at least in Celsius, but you have to change it to Kelvin.
Very good. That's what I was looking for.
Oh, I see.
Yeah. Okay. Plus MLV 373 Kelvin. Okay. So MCV log T final over T initial MLV over T final. All right, this is getting crowded, so I'll go to the next page. So that's the change in entropy in taking 50 grams of water. So 50 grams, and the specific heat of water is 1 calorie per gram per degrees Kelvin or Celsius. 373 divided by 293 plus 50 grams and 540 calories per gram. Okay, and then we'll convert that calories to joules in a second. T final is 373 degree Kelvin. Okay. So let's calculate this number. This is in, see, the grams cancels, and what you get is calories per Kelvin. Notice, see, this is the change in entropy when you heated the water from 20 degrees to 100 degrees. And this is the change in entropy when that water turned into steam. So most of the change in entropy occurs, most of the disorder occurs during phase change. Okay? All right. And then 0.184 joules per calorie, yeah, or 186, or whatever. Okay, so that was the change in entropy when you took 50 grams of water from 20 degrees to and boiled it all away. Okay. All right, so this problem says a 300-watt heat pump. What does a heat pump do?
Takes heat from a cold area and puts it in a hot area.
Right, just like a refrigerator, except that the heat pump is getting heat from the outside now and putting in here. Okay? So that's what it does. Operates between the ground whose temperature is 0 degrees Celsius and the interior of a house that is 22 degrees Celsius. So, for instance, in Florida, do you guys know what is the average temperature in Florida?
100 degrees?
You're funny. Huh? Okay, so here's how you tell. What, do you guys know what is the temperature of spring water?
72.
Very good. So you want to find the average temperature of a place, you dig a 4 feet hole and measure the temperature. So the average temperature in Florida is 72 degrees. Okay. So you can extract heat. Well, heat would, in the winter, heat would flow from the ground into your house, but you can extract heat from the ground and dump it into your house. Yeah. And in the winter, extract heat from your, in the summer, extract heat from your house and dump it into the ground. Yeah. Anyway, okay, so 300-watt heat pump operates within the ground whose temperature is 0 degrees Celsius and the interior of the house at 22 degrees Celsius. What is the maximum amount of heat per hour that the heat pump can supply to the house? So whenever they say maximum, then they're talking about an ideal heat pump, which is a Carnot heat pump. Okay. And the COP of a heat pump is the same as for a refrigerator, which is a QC over W. And QC is W is QH minus QC. And for a Carnot, max is, this just depends on the temperature. For an ideal heat pump, QC, QH minus QC is just TC, TH minus TC. Just depends on the temperature, just like for a Carnot heat engine. Okay, so COP max is TC is 0 degrees Celsius, 273 Kelvin, and TH is 295 Kelvin minus 273 Kelvin. So the maximum COP okay. And COP, of course, is Q divided by W. Okay, so what is the maximum amount of heat per hour that the heat pump can supply to the house? Okay, so QC is COP max divided by work. Okay, so QC over time is COP max over W over time. Okay, I'll do time as little t. I don't want that to be confused with temperature. Okay, COP max is 12.4. And what is the work done per second? 300 watts. Okay. Okay, 3,720 watts. Okay. So that's the amount of heat it's extracting from the 0 degree temperature. Okay. How much heat is it dumping into the house? The amount of heat it's dumping into the house is QC that it extracted plus the work done that gets converted to heat as well, and that gets dumped into the house as well. So that's 3,720 plus 300 equal to 4,020 watts. Okay. And they want you to find what is the maximum amount of heat per hour that the heat pumps can supply to the house. So the amount of heat per hour, that's per second, so per hour equal to 4,020 joules per second and 3,600 seconds per hour. Why are you having to supply this much heat? Because it's leaking out your windows and through your leaks and stuff like that. So you need to constantly supply the heat, to maintain that temperature.